Okay. That suddenly got louder. All right. So yesterday we talked about step index logical relations, which allow us to define these well-founded relations, give us basically an induction metric so that we can define well-founded relations that then we can use in order to prove type soundness for a language with recursive types. So I still basically have all of the definitions from yesterday up on the board for the logical relation at least. As we go along, I might put a little bit more up there. Actually, maybe as a reminder, I should put it up here. Right, we are now working with STLC, simply type lambda calculus, with recursive types. So the types in our language are Boolean, function, and recursive types. And then just as a reminder, the expressions in our language are the usual variables, lambda application, et cetera. But we added yesterday fold E and unfold E. And we added typing rules for these and operational semantics for these. The basic idea is that you always evaluate the E down to a value. Fold V is a value form. When you have an unfold E, you evaluate the E down to a value. And then the interesting reduction rule is this one. Unfold of a fold of V steps to a V. All right? So I'm not putting the rest of it up. It's in your notes, hopefully, from yesterday. What I'd like to do is just kind of, finish up with this basic idea of step indexing. Let me start by sort of opening it up to questions. I drew a bunch of timelines as I was, explaining things yesterday as to why there are, certain J's and K's, why something gets lower in certain places. But if there are follow-up questions, I'd be happy to take them. And then I'd like to start, I'd like to do one more proof, the proof for fold, for the fold typing rule. So one more case of the fundamental property that we've been proving. Yeah.
I just want to make sure I understand with the step indexing we're doing.
Yeah.
The idea is that we're able to do a proof over all possible indices, kind of like a limit.
Yes.
Okay.
Okay. Right here, right? So at the very top level, when we say, what does it really mean for an expression to behave like a type tau, given assumptions about its free variables types, right? This is that top level semantic definition about behavior. Here we say, for any arbitrary natural number, right? You have to be able to prove that if you get a substitution that is well behaved for k steps, then after I plug in all of those values from the substitution into my program and get a closed program, that program will behave well like a type tau for k steps. And this is an arbitrary case, so you can pick as low or as high a k as you want to. Basically, if at lower k's your program does not terminate, then you might not be able to tell whether the expression really behaves like a type tau. But because we're doing induction over all possible k, you will ultimately be forced to prove, for a very, very high k. If the expression does terminate, you will be forced to prove that it gives you back a value that belongs, right? This happens in this definition. You will be forced to prove that if the expression does eventually terminate, right, reach something irreducible, then it is a value form that behaves like a value of the type tau for some remaining number of steps. So if you pick an arbitrarily high k, you will get there in terms of its full behavior. Unless you have a non-terminating program, in which case it just looks fine. It looks like anything looks like a type tau. So we're good, right? And that's kind of interesting, what I just said. That's interesting in terms of what is happening right here, right? It says, okay, you picked a k, now pick a j that's strictly smaller than the k. And if the program terminates in that many steps, then I have to show, not terminates, but like reaches something irreducible in that many steps, then I have to show that it's a value. But if it just doesn't, then I don't have to show anything. We're good. Okay?
I have a question.
Yes.
Maybe we can take it offline if it is too. So
Okay.
you mentioned the motivation of step indexing.
Yep.
But I am still confused about the motivation of step indexing.
Yeah.
Because as we know, logical relation has been done for 30 over 40
Yes.
years before step indexing.
Yep.
And actually also the first version was for the untyped lambda calculus, which contained non-terminating program.
Yep.
So what is exactly that the step indexing brought us?
So basically the history, okay, so the question is, why do we need step indexing? We had logical relations for years and years before step indexing was created around 2000. So let's talk about the history of that, right? So basically what this technique is doing, I mean, here I'm showing you logical relations where when I talk about the behavior of a program, I talk about running it and seeing what happens, seeing what it does. That's how I get to the word behavior. But in a lot of the logical relations before that, people would try to essentially give mathematical interpretations to these types, right? They weren't running the programs most of the time. For the simply time lambda calculus, you can just run the program and it'll be fine. But mostly the work prior to step index logical relations was not for any kind of somewhat advanced typing feature. People would not use, the operational semantics as the way to assess the behavior of the terms. They would give you interpretations of the types of the language as mathematical objects. So what happened is that as you added more and more advanced features, the mathematical objects became more and more complex. And this was like sort of the time everyone was doing denotational semantics. Denotational semantics was where you give mathematical interpretations to the programs in your language, right? And then you try to do these proofs, but with math objects in there. People were doing these kinds of models, but basically what would happen is that, here's a model for a language with recursive functions. Okay, we're dealing with certain things, maybe CPOs come into the picture, et cetera, right? Like, here's a model of something with recursive types. Oh, okay, things get more complicated. The mathematical objects are more complicated. Now maybe I want to add in mutable references. Well, I just don't know how to do it at all. I'm going to do it only for mutable references, and I don't know how to handle the other features right now. Oh, now let's do polymorphism and predicative polymorphism. All right, here's a mathematical model which gives you a good interpretation for your language when it's STLC plus polymorphism. And then you say, oh, can I put it together with my thing which has recursive types and mutable references? And it's like, I don't know if the same mathematical objects will work. That was the problem, all right? And in the 80s, we sort of started to, like, the denotational semantic stuff just started to get so complicated. We wanted to be able to handle all sorts of language features, the features that practical languages actually have. They all allocate memory, for instance. Today, I'm going to talk about mutable references, so this is a great segue into that, right? I remember being a PhD student around then and looking at models that were based on game semantics. And Samson Abramsky was working on some of these. And I was like, Samson, you have a model of, I think there was a model of mutable references that someone else had done, and Samson had done one for polymorphism. And I remember standing at this conference Lix and saying to him, can you put them together? And he and someone else who was an expert in game semantics then sat there and kind of discussed, would it be possible? So I'm just giving you an instance of how this was really hard. Putting things together was difficult. What step indexing did for us is it gave us one little induction trick. And today I will show you one extra bit that's needed, but it still remains induction and step indexed. That just seems to work for all kinds of circularities that come about. And we never do anything different than run the program. That's the beauty of it. It's just been simpler. Is that a good enough answer? Yeah? Okay. And that's kind of the story of, what came before. I should also tell you a little bit about who invented what. So step indexing goes back to a paper, I believe 2000 or 2001. The work was being done around 2000, but I think the paper was published in 2001, TOPLSS. And that paper is an indexed model of recursive types for foundational proof-carrying code. It was by my advisor, Andrew Appel, and David McAllister. Back then, we still did not know how to handle mutable references. Mutable references, I'll show you today why they're so hard. And mutable references were basically my PhD thesis. That was 2004. Mutable refs. And then we kept going. In the years that followed, we figured out how to take type systems that have other features like substructural type systems, where you have linearity, linear types or affine types, where you can reason about resources. A couple of years later, Andrew, my advisor, went back to dealing with concurrency, and you realized, oh, wait a second, this is the same kind of circularity that was hitting us when we were doing mutable references. Oh, wow, we can use step indexing here as well. So, so now it actually is the foundation. It is the essence of how you prove certain program logic sound. How many people have heard of Iris? Okay. So the foundation of Iris, the later modality that sits in Iris that ensures that a lot of things are well-founded, the whole justification of that is step indexing. Under the hood, that's what it is. That's how you prove the logic sound. And the later modality to me is nothing more than, oh, take K and subtract 1. That's all it is. You know, it's just a different syntactic way of writing that. So yeah, it's basically helped deal with a lot of circular.
So but basically, if I rephrase,
Yeah.
it's an operational base
Yes.
way of defining logical relation,
Yeah.
and basically we can then use the indexing as the inductive structure based on the operational.
Exactly. And actually, there's a little bit more to say here, right? So what Marco just said, sorry, I'll repeat for the for the video. You know, that basically it's an operational base for giving the interpretation of these types, and the steps is just a trick for defining these relations which are about running the programs, right? Defining these relations inductively. Now, there was a little bit of a period of time when people were referring, you know, there were denotational logical relations, which were giving mathematical interpretations to things. And people like Bob Harper and Lars Berkedal initially, and then Carl Crary, there were a couple of papers, Harper Crary and Harper Berkedal, I think. They were trying, maybe I'm getting Berkedal wrong. I know at least Crary and Harper did this. They were trying to define so-called syntactic logical relations. They called them syntactic because they were taking this syntax of programs and running them. But the thing is, when they tried to scale it to recursive types, they couldn't because they didn't have step indexing. What happened instead is when they got to this particular definition, imagine if there are no steps here, right? It would be the definition from yesterday where I showed you, oh, the induction is on the types, but now we're using a bigger type. So now you have, if you define your logical relation that way, and it's not obviously inductive, the way it's written down, then you have to show that it is inhabited. Otherwise, it might be the empty relation. You might have defined something completely nonsensical. And then they went and they tried to borrow from denotational semantics techniques, where Andy Pitts had a technique called minimal invariance. They invented syntactic minimal invariance and tried to show that the relations were inhabited. The work to show that the relations were inhabited is huge. You don't want to do that. So basically, you know, that's yet another story for how people were trying. You know, this certainly was not the first instance where someone was running programs to talk about behavior, but they weren't obviously well-founded relations. So everything, you know, ultimately the math got very, very complicated. And here the math remains relatively simple. You know, you can always kind of think in terms of sets at the end of the day. Okay? I mean, these are sets of values, or until yesterday, they were sets of values. Now you can think of them, I put an index K here. You can think of them as sets of NAT, oops, wrong side, cross closed values. Instead of just, you know, power set of closed values, it's a power set of NAT cross closed values now. That's what types are, the interpretations of types. But, you know, they're still sets. So things stay simple. All right? Okay, so let's jump ahead. I wanted to go into history, so that was a perfect question. All right. Okay. All right, we're going to do one proof, the fold case, for the fundamental property. And then, hopefully, then after that, I'll start talking about mutable references. What my goal there is basically, by the end of today, I'd like to at least show you why mutable references are so difficult to give interpretations to, and what we had to do, because you can still use step indexing, but it's a harder problem. And I'll show you what the model looks like when you try to do it with step indexing. I probably won't have time at the end to like do proofs and stuff, but I want to show you the basic structure. Okay, so let's do, we've been proving the fundamental property, right? This theorem that basically says that if E is well-typed syntactically, then we want to show that it is well-typed semantically, right? And we've done a few cases. Did you guys do the application case yesterday? That was homework? You should do it. Work through the application case. That one is really like, you know, it forces you to unfold definitions at just the right times and piece all the little parts together. Okay, so we're going to prove this. And again, yesterday, of course, I didn't prove anything with the step indices there. So that really means that if we want to prove the entire fundamental property, we have to start over right now. Let's do the proof with these definitions for the variable case, true, false, if then else, lambda, and application. All right? Yesterday, I was asking you to do application for just the STLC logical relation, where we didn't yet have step indices. But you should try the one with step indices as well. Okay, so I'm just going to do the proof case for fold. And as homework, I am assigning you the case for lambda, okay? The step indexed one for lambda. Okay, so the fold case, we know we have fold E, it has type mu alpha tau. If under gamma, E has type tau with mu alpha tau for alpha. Okay? All right, so we want to show this, right? So show that under gamma, double tensile now, fold E has type, semantically has type mu alpha tau. Okay? So let's look at our definitions. What do we have to do? We have to start by saying, suppose I have some k that's greater than or equal to 0. Suppose I have some substitution that belongs to gk gamma. Then I have to show that gamma of fold E belongs to the appropriate type, right? So let's do it here. Suppose k greater than or equal to 0. Suppose gamma is in gk gamma. And show that gamma applied to fold E belongs to E for k steps at the type mu alpha tau. Right? I'm just specializing the definition to my case. All right, what am I going to do right here? You've seen me do it twice now, so tell me what to do. Push it in. Push the substitution in. All right. So needing to show this is equivalent to showing that fold of gamma E belongs to E k mu alpha tau. Okay? Good. All right, so we need to show that. All right, if we need to show something belongs to the E relation, let's see, what do we have to do? We have to assume that our expression reaches an irreducible state in some j less than k steps. All right, let's put a little line here. So now we get to say, suppose fold gamma E. Wow, that board is just walking up on its own. All right, gamma E reduces in some j, I'll put the less than k here as a reminder to myself, in some j less than k steps, reduces to some E prime, and E prime is irreducible. And then to complete our proof, we will have to show that this E prime belongs to V for the remaining k minus j steps, right? Just reading off of the conclusion of that E relation at our type mu alpha tau. Okay? So whatever this fold expression reduces to, we will have to show that it's a value that belongs to this mu alpha tau. Okay. Now, first, let me make an observation. We know what the operational semantics of the language is doing. It's call by value, right? So if fold gamma E, where this is an expression, reduces to something that can't take any more steps, then that means that it must have been the case, it's a deterministic semantics, must have been the case that this gamma E reduced to some value before that, right? It must have happened. Okay. So I'm going to say that by the operational semantics, by inspection of the operational semantics, if you will, we know that it must have been the case that gamma E reduced to something in some J1 steps where J1 can be less than or equal to our J, right, to some E1. Like this is just a sub-computation of this one, right? Those are steps. So this thing, so this is like we started running fold of gamma E. Surely the gamma E first reduced to an E1 That may be the actual thing that is irreducible now, or it may not be. Maybe there were more steps that happened after. We don't know, but we know that at least this much happened, right? These steps must have happened. And this one would be irreducible. Okay? All right, so either we got stuck here, which means that this expression is a fold of a stuck thing, fold of an E1, right? Or maybe we reached a value, but we're not ready to say that yet. Okay? All right, so we know that much. So if we know that much, what happens next? Let's speed this board up. It's going to keep running. Okay, let's go figure out what is our induction hypothesis. Well, we are doing that. There's our typing rule. So by the induction hypothesis, what do we know? What's in the premise?
That gamma entails that E is of type a tau, mu alpha tau substitute, yeah.
Right. You're just reading off the premise of the typing rule, but I'm replacing it with a double turnstile, right? Because that's what the induction hypothesis gives us. Because the theorem says syntactically well-typed, it means semantically well-typed. Since we know that this E is syntactically well-typed, therefore, by the induction hypothesis, since it's a smaller derivation, and the proof is by induction on the typing derivation, we have this. Okay, so since we have this, and this has a definition, we can instantiate that definition and see what it gives us back. All right, so we can instantiate this with our K. Let's just use our K. You know, the one that we started out assuming is greater than 0. We have a substitution little gamma that does belong to GK this. So instantiated with that and instantiated with the gamma, noting that the gamma is in G of gamma. So we're satisfying this, and we therefore get to conclude this fact. So therefore, after instantiating that, we get, therefore, that gamma applied to this E belongs to the E relation for K steps at this big type. Tau with mu alpha tau for alpha. We have that now. Good? So if we have it, let's use it. If we want to use it, what do we need to do? We need to say, oh, the gamma E gets to something irreducible. If we can provide that, then it will get something back. All right. So if I want to instantiate this, I have to show that this thing gets to something irreducible. Does it?
You said so. Yes.
Yeah, right here, right? Okay, so good. Therefore, I'm going to instantiate this thing with our E1, which is irreducible. Because here, right? Okay, so because gamma E reduces to E1, which is irreducible, we know that our E1 that we just reached belongs to the value interpretation of this big type. Therefore, our E1 belongs to the value interpretation for how many steps? I'll let you figure that out while I write this. I didn't say well, how many steps I instantiated this with. How many steps does it take for gamma E to reduce to E1? J1. All right. So, okay. So, if we had instantiated this thing with, if we have a K here, then what do I put here?
K minus G1.
K minus J1. Right. Exactly. Okay. So now we have this. All right, what did we need to show? We needed to show that fact that whatever fold of gamma E it reduces to this E prime in J steps, we needed to show that that E prime is in mu alpha tau. We have something about this E1. But let's make a note of something. E1 belongs to a value relation, right? So let's stop calling it E1. It actually is a value. So I'm just going to call this guy a V1, all right? So in other words, we've now concluded that whatever this reduced to is in fact a value. I'm just going to say we now know that this is a V1. Okay? And we know that that particular V1 belongs to this big type, the unfolded type. Okay? So then, it seems that what we need to show is that fold this reduces to this, right? So by the operational semantics then, if gamma E reduces to a V1, then fold of gamma E reduces to you guys can figure this out. Tell me by the time I get there. Fold? Fold V1. And in how many steps? Gamma E reduced to V1 in J1 steps. Yep. We just found out something else, that J and J1 are equal. Right? Okay, because fold gamma E reduces to fold of V1 in J1 steps. Fold of V1 is already a value. It is irreducible. Therefore, it must be E prime. This is our E prime from the very beginning, the one that we know is irreducible. And now we have to show that this particular E prime belongs to V of mu alpha tau for K minus J. Are you guys with me, or is it too much for the last lecture? All right. Yeah?
I have one question about the E prime. I couldn't quite follow why the E1 is irreducible if we only do J1 instead of J steps.
Ah, okay. So all I'm saying is that if you look at this particular reduction, fold of gamma E, you know you have to reduce this first, right? So basically it's like this. We started out reducing, I'll write it over here. We started out reducing fold of gamma E. If we start taking steps, it has to be here. So this will end up being rewritten to fold of eventually something that can't take any more steps. Are we okay with that assumption? Because we know that the whole thing is reducing to something that can't take any more steps. So it seems like a fair assumption that this will get to something that can't take any more steps. Okay? And now either this whole thing is going to be our final E prime, because if this can't take steps, then this fold E1 can't take steps, right? Or maybe we'll get lucky and this will be a value and something else. I don't know, but like this is how much we're willing to say so far. And the other thing that we're willing to say so far is that if this reduces eventually in J steps to something irreducible, then, and this might be that irreducible thing, then maybe the J1 and J are the same, but we don't know. But we know that J1 has to be at least less than or equal to J. We don't, it might be strictly less than, it might be equal. Through all of this reasoning, we then figured out that it was actually equal. Often in these proof cases, it might be strictly less than. Here, that's not the case. Yes, sure.
So we're concluding that like it takes a certain number of steps to get to something irreducible. So
Yeah.
in our like effect relation, or sorry, not expression relation.
Expression, yeah.
We say for all J less than K, I take this many J steps and I get to something irreducible.
Yep.
Are we saying then that there's only one J that'll ever satisfy that, and we're just keeping it arbitrary?
Well, for this definition, we're keeping it arbitrary. We're saying if there is, you know, for any possible J such that you've reached an irreducible state. Because it's a deterministic semantics, once you have a particular E that you are looking at, it will be and it does terminate in less than K, then you will have a particular J. Your observation is absolutely correct. The definition is just written generically with respect to whatever the J might be for your expression. Okay, so let's come back. What do we need to show now? We need to show that fold of V1 belongs to V of mu alpha tau for K minus J, where we know that J and J1 are the same. All right, let's go read the definition of V of mu alpha tau if we need to show something is in it. If we need to show that something is in it, then here's what we need to show. Oh, by the way, I tweaked this. Sorry, I didn't mention that. Yesterday, I showed you a definition of mu alpha tau, where I said, okay, it suffices for the V, for fold V to belong to mu alpha tau for K steps, it suffices for the V to belong to the expanded type for K minus 1. I meant to mention this at the beginning, that it's equivalent to write this in a more generic fashion. Just say for any J strictly less than K, it makes certain other parts of the proof just slightly easier. I'll get to that property in a minute. Oh, I should have gotten that property earlier. We're going to need it now. Okay. So this is just a slightly more general version of what I showed you yesterday. We still are strictly lower in our use of this definition than we are here, right? Because j is strictly less than k. Okay, so let me get to what I just realized I haven't mentioned, which is that we know, okay, let's write down what we have to show, and then we'll see why we need the property. So now we need to show that fold V1, well, we actually know that already, right? Fold V1 belongs to this for k minus j steps, which means that we need to show that for any arbitrary j prime, I'll call it j prime, strictly less than k minus j, we need to show that the V1 that's sitting under the fold, right? I'm just expanding this definition out. I'm here. I'm saying let's not call it j, we'll call it j prime. It has to be less than our k minus j for the proof that we are doing. Therefore, we have to show that our V1 belongs to V of the j prime at the expanded type. Doubling these. Okay. J prime is strictly less than k minus j. We need to show that V1 is good at this type. But all we knew before is that V1 is good for k minus j1, which is the same as k minus j. So somehow now I know that it belongs to this set for k minus j, but I need to show that it belongs to the set for fewer. And even if I left the definition to what it was yesterday, it would still be -1, so it would still be fewer, right? What I haven't shown you is a property that we need to prove before we start proving these cases of the fundamental lemma, but I did mention it yesterday, which is this property called monotonicity. If a value behaves like a type for k steps, then you have to be able to prove that it behaves like the same type for fewer steps. Okay? All right. So let's just write that down. In the early papers, we used to call this downward closure, so I'll write that down as well. That the sets that we're constructing are downward closed, that when the step index goes down, things are still in the set, okay? So if you look at some old references, you'll often see it called downward closure. All right, what does it say? It says that if you have a V that belongs to V of k for any arbitrary tau, then for all j less than or equal to k, you can make it strictly less than if you like, doesn't matter. V belongs to Vj. Okay? Monotonicity or downward closure. This is a lemma you have to prove about every single type in your language, right? Because it is about all the types. Basically, what it forces you to do is it forces you to go look at every single the V relations for every single type, and for every single one of these, you have to prove that the property holds. Okay? So if Booleans belong to bool for k steps, they clearly belong to bool for all fewer steps because the definition isn't even doing anything with the steps, right? Functions are interesting. This is what I talked about yesterday. I want you to do the proof of monotonicity for the function case, okay? It'll go through, but if you had done the definition of functions differently, if instead of all of this, you had said, oh, for all of lambda belongs to this, if for all v that belong to tau 1 for k steps, then I can go ahead and do the substitution, and ev for x belongs to this for k steps. Try it out with that one. You will fail. You will not be able to prove monotonicity. It has to do with this interesting thing that these functions are, contravariance of function arguments. If you don't advance the clock, so to speak, before you do the application, you will fail to prove monotonicity. It's really interesting. You should try it with this, okay? And then do it with the actual definition. But this was something that we had to think about back when we invented this stuff. all right? It didn't just fall out. So it's sort of like lessons learned through getting burnt, or proofs not working out. Okay, then let's see. Okay, and then we can prove it for fold V as well. You can see it really, really easily. If it belongs to this for K steps, then already the definition, I gave you a more general definition today, from which you can instantly prove that, of course, for anything smaller, it belongs to the thing, belongs to the type. Okay, so I'm going to assert that for this type, I do have monotonicity, and that basically lets us finish our proof. Why? Because we know that V1 belongs to V of tau with mu alpha tau for alpha for K minus J steps. The fact is right here. We need to show that it belongs to the same type for J prime fewer than K minus J, follows by monotonicity. And we are done. Okay? So you saw a mix of things being used in here, right? Like we appeal to the operational semantics. We look at, because we're talking about how the terms behave by running them, right? So we have to make certain conclusions about, or inspect the operation in some sense, right? I did that to figure out, well, this must have reduced, et cetera. And then it's an interesting interleaving of when do you apply the induction hypothesis, et cetera. Yes? Okay, I don't want you to think about every step along the way, because that is a very progressy kind of thinking, you know, progress and preservation kind of thinking. Don't do that. Instead, the sentence I've been using all along is that if you have K steps to observe or interact with a value, that means you can run it, you can interact with it, you can apply it if it's a lambda. By interact, I mean like if it's a lambda, then I'll apply it. If it's a pair, I'll maybe extract some of its components and inspect them. Maybe I'll extract the components and I'll get some functions back and I'll then apply them, right? That's what I mean by interact with it, use it. All right, so what I'm saying is a value belongs to, behaves like a type for up to K steps. That means you have a budget of K. That means if you had a lower budget, then obviously you have less interaction power. Right? You have fewer steps in which to like prove that, oh, you're not that type, right? That means you can observe only less. So if it looks like it has that type at 100 steps, then obviously at 50 it must have looked like it, because, you know, it's only when you add more steps, when I give you more steps, if I gave you 150 steps instead of 100, you might be able to tell that something sitting under there, which has a complicated lambda type or function type or something, is not actually that type, because you might feed in an input and then get it to like get stuck, you know, crash basically. So that's the intuition. It's not about the steps along the way. It's about, oh, my overall budget is that and it still looks like this. I haven't been able to prove it wrong, right? Or prove that it's not good. So obviously I need more steps to prove it's not good. If I have fewer steps, then of course it's still going to look good. That's the intuition from monotonicity. Okay. I don't know who was next, but yes. Yeah. Where do we use the assumption that J is strictly less than K? Are you talking about right here? Okay, it's not that we use the assumption. I mean, we use it to visually inspect our relation and say to ourselves, look, it is defined by induction. And then, of course, you use it when you go and do your proofs by induction. There are certain proofs where you will want to do outer induction on the step index and inner induction on the type. Okay, but here, basically, the way that I explained this yesterday was I said, these relations are inhabited, as in they're good sets. They're not empty relations, because you can write down any kind of definition for relations, right? Oh, this relation contains all of these things if they have this property. If the property is not satisfied, then the set is empty. Okay, so so when we define them inductively, we can start to see that they are not empty, is the point, right? So initially, until yesterday, before step indexing, they were all defined by induction on the structure of the types. So bool doesn't use anything. Tau1 or tau2 only uses V relation definitions for the smaller types tau1 and tau2. So they're getting built up out of smaller definitions. This was the first one where suddenly we were talking about the definition of something that's of a bigger type. So we supposedly haven't constructed that set yet if we're constructing them inductively, right? So we said, now we're in trouble. This might not be inhabited. We haven't constructed the bigger set yet. Okay, so that's why we brought in an induction metric. And I said the induction is going to be on the step index first. And in our induction, if the step index stays the same, then the type should go down. Roughly, you can think of it that way, right? So that's the way in which we are using it. Okay? Yes?
I know this is a little bit after the fact, but could you clarify once more why J1 must be equal to J2?
Okay. Gamma E, so fold gamma E is what we're running.
Yes.
And we said that this gets to fold of some irreducible E1 in some number of steps J1 that I said, I don't know, all I know about it is that it's less than or equal to J.
First, I should ask. We
What?
are not arbitrarily choosing this J1? We are
No, we're saying there must be one.
Okay.
Yes. So when I did this step right here, I said, oh, this reduces to something irreducible. That means that its sub-expression, this guy, must reduce to something irreducible in some number of steps. And all we know about, so this is this is sort of like there exists a J1. And all we know about that J1 is that it must be less than or equal to J.
Yeah.
Good?
So,
Okay. Yes.
follow-up. So is the whole reason for that rule because or the confusion for that rule just because we are narrowing the gamma into the fold? Or I mean, bringing the gamma into the fold?
We're just bringing the gamma into the fold because I know that ultimately I want to use my induction hypothesis, and that's going to give me my induction hypothesis, it's going to give me some fact about a gamma E. I'm just anticipating that.
Okay.
And that trick almost always works. If you have E1 applied to E2, push the gammas in, gamma E1, gamma E2, because by the time you get to, oh, I have an induction hypothesis, what do I instantiate it with? You know exactly what to instantiate. It just, the pieces fall into place.
Okay.
Yeah. Yeah?
You only mentioned monotonicity on the values. Does this imply monotonicity for the other ones as well?
You mean for the E relation?
Yeah.
You don't need it.
But like if you wanted it, would that be true?
I hesitate to say because I think it depends slightly on how you define it. I don't want to do this like standing right here. I can do it right after. Because I have had this discussion a little over a decade ago. And I was like, well, if you define it like that, then it works better. If you don't, then but even back then, the answer was you don't need it for the E relation, but we can check if this definition is doing it. Yeah.
Just for the recording, maybe you could repeat.
Oh, sorry. The question was that I have defined this monotonicity lemma for the value relation, but does monotonicity hold if this was the expression relation? Okay? And the answer is that, yeah, you don't need it for the proofs anywhere, but if you were interested in checking if it holds, just do it with that definition, see if it holds. Okay. Oh, yes. So say the first part of the question again. If we did have? Okay. So if we did, the question is if we did have monotonicity for the E relation, then would this be analogous to preservation? If you picked an arbitrary K. Okay, so the issue is that what preservation says is that if you start out with a term and you run it, you take 1 step, 2 step, 3 step. After every single one of those steps, whatever term you have now reduced to or run to, you will be able to construct a typing derivation for it. And we're not, this isn't saying anything about constructing typing derivations for it. But I know why you're asking. Because what this definition is doing is, even though it's not constructing syntactic typing derivations, what it's doing is it's saying that there's a semantic invariant that holds with all of those steps. Okay? And it is making sure that that semantic invariant is preserved no matter what the K. So your intuition is right. It's just that technically speaking, it's not the preservation lemma that I wrote on the board, right? But it is a semantic version of that, in a sense, in some sense. Yeah. Okay. That's actually it's very true. I mean, because that's what we're doing overall, right? Like, if you think about it, we're saying syntactic implies semantic, right? It's just that this definition is taking the construction of syntactic typing derivations and instead replacing it with invariants that hold when we run. And that's it. And that of course, is showing up here. The definition is preserving that with every step that you take. Like, as you reduce steps, oh, my invariant still holds. Something is being preserved. But it's the semantic invariance instead of syntactic typing. One advantage of this proof method, actually I'll get to it in a second, is that when you get to complicated languages which have like mutable state or just weird state things going on in the program, like there might be a heap, etc. When you do a progress and preservation proof, you have to give yourself typing rules which you will only use to type check running programs. Those, like for example, a location is not something that exists in a surface program. Right? So in all of those languages where certain objects come into existence after you start running, if you're doing a proof using progress and preservation, you need to give yourself typing rules that know how to type check those runtime objects. With this method, you don't. That's a very important distinction. It basically means that in a progress and preservation proof, a lot of the complexity is going into designing that type system that can type check those intermediate runtime objects. And here the complexity is in talking about, so what's semantically happening with those runtime objects and what are the invariants that need to be preserved. So it's not that it's just like free, right? It's just that the complexity goes from one place to another. Okay. Alrighty. Let's talk about mutable references. I'm not going to get very far, I think. But how many people have seen kind of a simply typed lambda calculus, perhaps, with allocation, read, and write? OK. So let's do this kind of fast, but I'll still explain for those who haven't. No. OK. So basically what I'm after is I want to take my simply typed lambda calculus. We can leave the recursive types in, but I won't talk about them for the next half hour. And I want to add the ability. I want to add the ability to allocate memory. So it's called dynamic memory allocation. I want to be able to allocate a reference cell or a memory cell and then store some value in it. This is essentially, something that languages like ML or Camel, Java, etc. Most modern languages have the ability to allocate data in memory, right? All sorts of data structures. So let's take the syntax of simply typed lambda calculus, and I'm going to add one type called ref of tau, which is the type of a reference or a pointer to a tau, okay, that lives in memory. And then I'll add some operations that let us create references and read from references and write to references. Okay, so so the types in my language. I had unit yesterday, still have bool, tau1, arrow tau2, and now we can have recursive types, but I'm just not going to write it. Ref of tau, okay? Ref of tau is the new type. It's the type of a reference. So some location, let's say, that I allocate in memory will have this type ref of tau. Okay. For expressions, we have all the expressions that we had yesterday for these earlier types. But now we want to, and for unit, I'm going to write it like this, etc. But for references, I need an operation to be able to create a new reference. In other words, create a location that will then be a location for a memory cell that contains some value of type tau. So I'm going to have new E. This basically says, create a new reference cell, evaluate this value E, and whatever value you get, store it in that reference cell. Okay? I'm going to have, this is written usually bang E, which means dereference E. Go and read, take E, evaluate it down. It better evaluate to a location, read the contents of that location and give it back to me. So this is read out of a reference. And then assignment. E1 gets E2. In other words, evaluate this down to a value. It better be a location. Otherwise, you're going to get stuck. Evaluate this down to a value, let's say some V2. Take the V2 and store it into the cell that location L points to. So if there was a V1 there, we're just going to get rid of it, and we're going to put our V2 there, whatever this evaluated to. Okay? Now, let's actually write down the operational, value forms. So the value forms are true, false, unit, lambda. But for references, we need a value form which is locations, right? So I've already alluded to this. I said, oh, go ahead and evaluate E. It better evaluate to a location. That location is a value, right? And then we can read out of that location value. Similarly here, this needs to evaluate to a value form, which is a location, and then you assign to it. Okay, so locations L are the new value form. It's the canonical form for references. Let's see, should I write down, would you guys like me to write down the operational semantics? Or do you think you kind of have the hang of it? Let's write down a little bit. Okay, so until now, in simply typed lambda calculus, we had no memory. So when we ran a program, the program was E, and running a program was simply, oh, E takes reduction steps to E1, to E2, et cetera, right? You just keep taking steps. That's the whole program. That's our whole abstract machine, if you will, right? Or program configuration that runs. Now, programs are going to have memory. You can call it a memory, you can call it a heap, you can call it a store, okay? But something that is a mapping from locations that has all of those cells that I'm talking about, right? Those locations that I'm talking about. And those cells have contents, stuff that you're going to store in memory. I'll just use the letter S for store, but H for heap and M for memory are perfectly acceptable, and you will see them in all sorts of papers. All right, so a program configuration that runs now, a program configuration that runs is going to look like this. It's going to be a store paired with the expression that you are running. Okay, the store here, so stores are basically they're just a sequence. They're a finite, they're a partial map from locations to values that are stored at those locations. Okay, so let me write it as store is basically a partial map from a location to a value, to a closed value. In fact, we're never going to put values with free variables into our store. So I'll write cval for closed value. Okay? Just a map. And often I'll just write this as, L points to some V is in my store S. Okay. So I want to give an operational semantics that will look, reduction rules that will look sort of like this, right? This will be a reduction step, SE steps to S prime, E prime. The interesting ones that I want to show you are, so lambda, for instance, if this was application, lambda XE applied to V, it would still step to, the store would not change, it would still step to E with V for X, right? So I'm not going to repeat those, because all the rules from yesterday remain the same. You just put S's there and leave the S's, the store is unchanged, because they weren't touching the store. So let's touch the store. Where do we need to do that? Let's say we have some store S, and we want to run new of a V. And I'm assuming that you've already evaluated that expression down to a V, which you will do with evaluation contexts, which basically tell you we have to add new E, we have to add bang of E, and we have to add E colon equals E2, as well as V colon equals E. What is that saying? Evaluate in this position first, evaluate under the bang first, evaluate on this side first, and once you have a value here, evaluate on the left. Right? So left to right call by value evaluation, still pretty standard. Okay, so now let's do the actual creating of a new reference cell. What we want to do here is we want to say, let's pick a fresh location L that is not in the domain of our current store. And then we will take our S and we will extend it with that location, fresh new location, maps to, it will contain, it will be initialized with, if you will, the value that I want to put into the new reference cell. And after we have allocated that, we give back a pointer to the new cell, the location of the new cell. Okay? If we want to read out of a cell, if I have a store and I want to read out of a location L, now the side condition is that L better be in the domain of the store. Oh, not in, better be in. In fact, I should just write it as L maps to V is in. If L maps to V is in my store S, then I am going to leave my store unchanged, and I'm going to give you back the value that was stored at that location. Okay? All right, I'm going to move up here for my last rule. If I have S and I want to write the value V into the location L. This is assignment. How do we do assignment? The side condition is, suppose that L maps to some V prime is all, we don't care what V prime is already in the store. Then go ahead, take the store, and do an update. This is now an update, not an extension. Do an update so that L now maps to this V. So we stored that there. So update the store so that L contains that value. But L was already in the domain of the store, right? And after we do assignment, we normally just return a unit because you already have the pointer to the location, so you don't need it again. So there we go. Just return unit. Was there a question? Yeah.
Do we return the old value instead?
We can always return the old value. I've just set it up so that I return unit. Yeah. Okay. If you return the old value, that's more like a swap instruction, which is not completely conventional in. So I just went with this. All right. So, oh, there's so much to be said about mutable references. Let me think. Now I'm doing lecture replanning. Okay. Yeah.
Maybe I'm mistaken, but do
Yeah.
we also need some form of a sequencing operator?
You can always do sequencing let using your lambda via application. So I'm just not showing it. But yes, it's in the, it can totally be encoded in the language, or you can add it as a primitive. It's not the thing that causes the complexity, so I'm just not going to bother. Okay. All right. So that's the operational semantics. So I'm going to just keep going at a decent pace. I don't want to skip things. Let me talk about. First, let's talk about when you have a language with allocation. I want to talk about something called type preserving updates. In languages like ML and Java, you can never change, once you allocate a reference cell, at the moment that you allocate the reference cell, the type of the value that you're going to store in that cell gets fixed forever. You're never allowed to update it. Why is that?
Just the size, right?
The size is a very good point. Yes. But what if I didn't even care about sizes for a second?
I think it's also related to.
Sorry?
I think it's also related to other multiple parts of the program using the same variable.
Multiple parts of the program having sort of pointers to the same locations, right? So let's look at an example. If I have a function f that takes two inputs, x that is a reference to a Boolean and a y that is a reference to a Boolean. Okay? Suppose in the body of this function, what I do is I say something like, suppose I allow you to do deallocation. Deallocation is also a form of changing the type of the cell, right? Because you're going to get rid of it. Okay? So if I was allowed to change the type of a cell, and I can change this to something else in a second. Suppose I free the x, this reference, and then I try to read out of the y. Now, if I pass you, when I call the function, x points to location L1 and y points to location L2, Sorry, this is L1 and L2. I need more chalk. L2 and L1. So if these two point to different locations, then of course if I free this, then I can still read out of this, everything is okay. But if I happen to call the function when x and y both point to the same location, then what just happened? We used after free, we crashed basically, right? Like, because this can't possibly work. So the question is like, what does the type system then need to do to track the fact that they are aliases or they are not aliases? This issue is called aliasing. Two variables are aliases for the same location. They are pointing to the same location, right? And you can always call this function with two things that point to the same location or that point to different locations. Another thing we could do is if I, strictly speaking, I started out by saying type preserving updates and then change my example to free, but let's do a type changing update. Maybe what I want to do is here, I have a reference to a bool, but I'm going to put a number in it. And then I try to read out of the y, okay? And maybe I want to use it in an if then else. Suddenly, if they are aliases, I change the type of the contents from a Boolean to an integer, and now I'm using an integer here, right? Because instead of whatever Boolean was in here, now I have the number 5. So that doesn't work, right? The if then else should crash because it's expecting true or false, not expecting an integer. I mean, I could also do this like I could store a function here, and now you're really in trouble, right? Okay, so so type preserving updates are a problem because of aliasing. Aliasing is a very difficult thing to keep track of in a type system. Rust does it very well, by the way, or keeps track of lack of aliasing. But that's for another day. So basically, a lot of these languages have type preserving updates. And what I'm going to show you is, I'm going to try to show you a logical relation for a language with dynamically allocated mutable references. You can update the contents of references, but we will require that all updates be type preserving, because that is typical of languages like ML and Java. And this was an open problem, you know, like how do we do logical relations for these languages with type preserving updates? And they can have all sorts of funky features. You can store functions in the store. You know, it's called higher order store when you can store functions in the store. All of these features put together like really form a very complex kind of picture from a semantic point of view. And I want to show you the other thing that is tricky. Right now on the board, I only have simply typed lambda calculus, which by the way is terminating, right? I told you that 2 lectures ago. All I did, let's throw out recursive types. I didn't put them on the board intentionally. All I have is mutable references. Do you think this language is terminating or non-terminating?
Non-terminating.
How many? Okay, never mind. All right, this language is non-terminating. You can create loops in this language, all right? And the most famous example, I feel obligated to show it to you, is this one. You can create a cycle and loop forever very easily. So you can construct a non-terminating program in this language as it's on the board. Basically, we can do something like let x equal create a new cell. What I'm going to do is put, let me just note that I'm going to try to create a reference cell that has type unitary unit. Okay, I'm going to initialize it with lambda z unit.z. Okay, so just the identity function. Takes a unit, returns a unit. So I'm initializing my cell, which x points to, with that thing. Now what I'm going to do next is I'm going to say, let f be a function that takes a lambda z of type unit. But then what it does, it uses this x. It's going to read the function that's stored in the location x. And it's going to apply it. I'll just apply it to this. It's a unitary unit function that I get out. So I'm just going to apply it to my unit input. Unit is really boring, right? But nonetheless. And then okay, then what am I going to do? I'm going to take x. I'm allowed to do assignment in this language, so I'm going to put f into. I'm going to update the contents of x. Instead of lambda z z, I'm going to put lambda z bang x z into that cell. And then we will end by saying, okay, let's start running this function. What does the program do? It loops forever, right? Because we had a cell. In order to create it at the very beginning, X is pointing to it, right? Some location. In order to create it at the beginning, we put a lambda ZZ in it because we had to initialize it with something. Our language always initializes with something. But we made sure the type was unit arrow unit. Then we created a new unit arrow unit function that could refer to this particular cell, right? And what that function is doing is it's saying, read the contents of this cell. So read me, the same function, and just apply me to unit. Right? So it's just going to read itself out every single time and apply itself to unit, and then it's going to do it again and again and again, right? Okay, it's going to loop forever. This program is a very famous program. It's called Landon's Knot. It's named after, it was, Peter Landon was the one who came up with this crazy, crazy example that once you have this terminating simply typed lambda calculus, and all you do is you add the ability to update your references, right? Dynamically allocate and update references, you can loop forever. So basically, you're creating cycles in the store, right? This thing right here, because it has an X there, is pointing to itself. That's another kind of circularity, right? With recursive types, we were seeing a different kind of circularity. With mutable references, it's these cycles in the store that are going to get us. Yeah?
Is there any sort of equivalence between the two constructs? Like, could we express recursive types using the store and vice versa?
No. They're different. Oh, can we express recursive types using the store or vice versa? Not to my knowledge. Maybe there's some weird trickery that I'm not thinking of, but not to my knowledge. I've never really done it. Okay. All right. So, Landon's Knot. Type preserving updates, cycles. My point with showing these two examples is that aliasing is evil. Therefore, for a simple type system, we want type preserving updates. And that's why OCaml, Java, they have garbage collectors to basically collect the garbage afterwards. You know, because freeing is like doing a type changing update. Oh, by the way, the opposite of type preserving updates is called strong updates. The phrase strong update, when you say I have a language with strong updates, what you're saying is that my language allows you to update the contents of a cell with a value of a different type changing updates. Okay, we normally refer to it as strong updates. Good phrase to know. All right, so in this weird setting, you have cycles in the store, because we store functions in them and create these Landon's knots, and we have type preserving updates. Now let's go and see how do we extend the models that we've been doing to handle the interpretation of a ref tau. Okay, and I'll just go for a little bit longer. I think we want to stop in 10 minutes is my understanding. Okay, so we're just going to attempt to do this, right? Before I attempt, maybe I want to show you one other thing. I want to talk about the kind of meta type of the type interpretations that I've been giving. So remember I said a little while ago, I said for simply typed lambda calculus, a type was just a set of closed values, right? So let's just make this a little bit more precise because it's going to become really important now. So on day one, a type, I'm using capital TYPE to represent the sort of meta type that contains all possible interpretations of types. Okay? So I'm going to say that this contains I. I is an interpretation of types. So on day one, I was just a set of closed values. Okay? So basically I don't have to write that. On day one for STLC, interpretations of types were just power set of closed value. Okay? On day two, when we added step indexing, type interpretations became a different kind of beast. Type interpretations now became basically a mapping from natural numbers, because my V relations are the things that are constructing type interpretations. But they said, give me a natural number, and then I'll give you the set. So we have to give it a natural number, and then it gives us back a power set, closed values, C-val. Okay, so that happened on day 2. Today, something more will happen. That will not be so good. But I just want to put that up there because we're going to have to go examine what happens with types. Okay, so let's create some space here, and let's just take a naive stab at, can we just take the step index model on the board and try to give a meaning to the type ref tau? And I just want you to use your intuition. What are the values that inhabit a ref tau? Yes? Label? Locations. I'm using L for location. Yeah, okay. So locations. So what should the definition say? When is a particular location L something that I can put in the set? When does it behave like a ref tau? Yes?
Given all stores where L points to a value of type tau?
Given all stores, so given
For all stores, yeah.
for all stores or for some store?
Not sure, probably for all.
S of L, the contents of the location, belong to perhaps something like V of tau.
Yeah,
And I don't know what K to put there, but we can figure it out.
or for all j less than k.
For all j less than K, we can leave it as a K minus 1 for now, but yeah. Okay. So the for all S is a problem. It's more like,
For the state we're currently in. Could it be like for the state we're currently in, we have some way of expressing that?
I'm not catching the first part of your
State
sentence.
we are currently in.
The state we are currently in, exactly. So basically what's happening is, a little bit of it was happening yesterday too. When I was doing step indexing, I said to you, let's figure out how we know that a lambda belongs to some type for K steps. And I drew the timeline, and I said, right now we are in a world where we have K steps left. And at this point in time, I need to know whether my lambda behaves like a tau 1 or a tau 2. That K is representing something about the state of the world right now. Okay? And these are, I said yesterday that these are called possible world semantics. But then I didn't really go on about it. Today I will go on about it. The K yesterday was capturing something about, some assumption, at least in our definitions, about what world we are currently in. The world we are currently in, K is the number of steps we have left. And when we move to future worlds, we have fewer steps left. Okay? Now, we can't answer the question about whether a location actually is a reference to tau without saying, I'm in a world where my heap or my store looks like this. If my store looks like this, now tell me whether the location does, in fact, behave like a ref tau. So we need a richer possible world semantics. We need a richer notion of world in order to make any kind of progress here. So we can't just do for all S. We need to say, not just in a world where we have K steps of execution left, I'm going to say, in a world, let's say, where we know that the current store looks like S. You're giving it to me. And this, again, is a naive attempt. It's not going to work. Your hand's going up? Yes?
Yeah, I was just going to ask a question, but you can finish it up. Sorry.
Okay. So I'm going to say, give me the current store. And in the current store, I'm going to try to answer the question of, does this location behave like a ref tau? Now, at least I have some hope of making some progress, I think. So we're going to say, all right, this is a location. If it needs to be a reference to tau, that means it needs to contain a tau, right? So we'll do basically what we were doing before, but we'll say in the current world, in the current store, if I read out the contents, S of L, I get the value stored there. Does that value better, belong to V of this type tau, the contents? And for step indexing, we can do something. I'm so flippant about that. We can do something like for all j less than K and put the j there. That was the original suggestion, right? But what does this get us? Remember, I keep saying that In order to decide if a value, like a lambda, behaves like a tau 1 or a tau 2, you need to say what happens when you use the lambda. Lambdas are only used by one construct in the language. That's application, right? Oh, I just realized I never even put up the typing rules. All right, let's put up the typing rules. New E gives us back a ref tau. If E is type tau, then new E is a ref tau. Under gamma, bang E. If E is a reference to a tau, then bang E will give us back the contents, so it will have type tau. And finally, assignment, E1 gets E2. E1 better be a reference to a tau. The thing that we are trying to write into it, our E2, better be of the same type tau. And then E1 assigned to E2 will have the type unit. Those are our typing rules. So then back to the thing I was just trying to say. In this language, what are the constructs that use a reference, the elimination forms? The last two, right? Because they're saying, if E is a ref, what can I do with it? If E1 is a ref, what can I do with it, right? So there are two ways in which we use reference types, two elimination forms for reference types. For lambdas, we just had one. What we have on the board right now allows us to check that what the store contains right now is, in fact, a tau, or will behave like a tau. So that handles this guy just fine. Reading is going to be no problem. But what are we doing to make sure that the reference behaves like a tau when it comes to assignment? The thing is, this definition somehow needs to capture that. Otherwise, you're not going to have much success. It needs to say that as the world moves forward in time, you will always, this location L will always contain a value of type tau. If we can do that, then we've sort of built in our requirement that updates be type preserving. Okay? And that's the part that is really hard to express. Many hands are going up. Yes, back there.
Are we still able to have monotonicity if we put definitions that are
Yes, because the way that we had monotonicity for step indexing up there, I'm going to read it as if the steps are worlds. I'm currently in world K, and V belongs to tau. In some future world, when I have fewer steps left, V belongs to tau. The world that I have given you right now over here is actually wrong. Okay, so I'm gonna erase that, and instead I'm going to say it is not, like this definition naively is a great first attempt, but it will only work for reading a value of type tau. It does not ensure that the language only has type preserving updates. So we need to do something more. What we're going to do then is, instead of keep the current store in the world, we're going to say the current world is described by a set of assumptions by basically what I will call a store typing psi. Psi is going to tell us, it's going to be a mapping from locations to semantic types. It's going to tell us, its domain is going to tell us all of the locations that exist right now. And in the future, we might have more locations that exist because we keep allocating more and more. Its codomain, right? It's going to map locations to semantic types. Its codomain is going to, for every single location, we're going to say, what type is it allowed to contain? That type better not change in the future. It must remain the same. That's how we will ensure type preserving updates. All right? But now, this is our world. Here, we want to say something like, psi of L better be equal to maybe k minus 1 tau. In other words, L behaves like a reference to tau if the current world tells us that this location will always contain something of type tau. And the rest we will see tomorrow. All right, I'm going to leave it with that cliffhanger. This is not going to be well-founded without a little bit of extra thought and work. And I can take one or two last questions, and then we will continue tomorrow. Any questions? Yes.